Here's what happens in the microseconds after a depleted uranium round hits armor. The projectile doesn't just punch through like a conventional bullet. Instead, it begins to fracture in a specific pattern that creates a sharper tip as it penetrates. Simultaneously, the friction generates enough heat to ignite the uranium fragments, spraying burning particles into the breach at 1,500 meters per second. As seen in 1991's Gulf War, this combination of self-sharpening and pyrohoric properties creates devastation that no other material can match. Watch how DU's physics outperforms every other projectile. But what makes this metal so fundamentally different from everything else in a military arsenal? The physics behind the devastation. The answer lies in a combination of physical properties that creates what military engineers call the perfect storm of penetration physics. At 19.1 grams per cubic centimeter, depleted uranium is nearly twice as dense as lead, letting designers slim down projectiles for greater speed. This density advantage translates directly into battlefield performance because it allows engineers to create projectiles with smaller cross-sectional areas while maintaining the same mass as larger conventional rounds. The aerodynamic implications of this density become clear when you consider projectile flight characteristics. A depleted uranium round experiences significantly reduced drag compared to a steel projectile of equivalent weight. This reduction in drag allows the projectile to maintain higher velocities over longer distances, preserving the kinetic energy that drives penetration. The smaller cross-section also concentrates this energy onto a much smaller impact area, creating pressures that exceed the yield strength of most armor materials. However, density alone doesn't explain depleted uranium's battlefield reputation. The real magic happens during the penetration process itself, where depleted uranium exhibits a property called adiabatic shearing. When a conventional steel or tungsten projectile hits armor, it tends to mushroom and flatten, spreading the impact force over a larger area and reducing penetration effectiveness. Depleted uranium behaves completely differently. As a depleted uranium penetrator encounters resistance, the intense pressure and heat cause microscopic fractures to form along crystalline boundaries in the metal. These fractures propagate in a specific pattern that actually creates a sharper tip as the projectile pushes through the target. The outer layers of the penetrator literally shed away in controlled fragments, continuously exposing fresh, sharp metal underneath. This self-sharpening mechanism allows the projectile to maintain peak penetration efficiency throughout the entire impact sequence. The physics become even more interesting when you consider the pyrohoric properties of uranium. When the self-sharpening process creates fine uranium particles, friction heats DU dust high enough to ignite spontaneously. This creates a stream of burning metal that follows the projectile through the target, causing secondary damage that conventional penetrators simply cannot achieve. These three properties work together in a time frame measured in microseconds. The dense projectile maintains velocity through air resistance. The self-sharpening mechanism maximizes penetration efficiency, and the pyrohoric ignition creates devastating secondary effects. The entire sequence from initial impact to complete penetration typically occurs in less than 0.001 seconds, but the physics involved create damage patterns that no other material can replicate. Recent 2025 research has focused on improving these natural properties through advanced metallurgy. Scientists have developed new alloying techniques that add trace amounts of molybdenum and titanium to enhance the self-sharpening characteristics. These additives create more predictable fracture patterns and improve the consistency of the sharpening effect. The latest generation of depleted uranium penetrators shows a 15% improvement in penetration depth compared to pure uranium rounds from the 1990s. The alloying research has also addressed one of depleted uranium's few weaknesses: its relatively low melting point compared to tungsten. New composite designs sandwich depleted uranium cores between tungsten sleeves, combining the density and self-sharpening properties of uranium with the heat resistance of tungsten. These hybrid penetrators maintain their effectiveness against reactive armor systems that use explosive charges to disrupt incoming projectiles. Tungsten alternatives have made significant progress in recent years, with new sintering techniques creating tungsten alloys that approach depleted uranium's density. The latest tungsten-rhenium composites achieve densities of 18.5 grams per cubic centimeter, nearly matching depleted uranium's performance. However, testing data from 2025 reveals that these alternatives still cannot replicate the self-sharpening mechanism that makes depleted uranium so effective. Independent testing conducted by defense contractors shows that tungsten penetrators lose approximately 25% of their penetration effectiveness after encountering the first layer of composite armor. Depleted uranium penetrators, by contrast, actually improve their penetration characteristics as they encounter resistance, maintaining nearly 100% effectiveness throughout the target engagement. Modern armor designers have responded to depleted uranium's unique properties by developing countermeasures specifically tailored to disrupt the self-sharpening process. The latest generation of reactive armor systems uses shaped charges designed to create lateral forces that can deflect incoming penetrators before the sharpening mechanism fully engages. These systems show promise against conventional rounds but remain vulnerable to depleted uranium's rapid penetration timeline. Composite armor designs now incorporate ceramic layers specifically chosen for their ability to create fracture patterns that interfere with uranium's natural shearing behavior. Advanced aluminum oxide ceramics can create stress concentrations that cause premature fragmentation of depleted uranium penetrators. However, these countermeasures add significant weight and cost to armored vehicles, creating design trade-offs that limit their practical application. The most sophisticated modern armor systems use multiple layers of different materials to exploit the different phases of depleted uranium penetration. A typical system might use a ceramic front layer to disrupt the initial impact, followed by a steel backing plate to absorb the energy from uranium fragments, and finally a Kevlar spall liner to contain any remaining debris. These multi-layer systems can reduce depleted uranium penetration by up to 60%, but they require armor packages that can double the weight of a vehicle. The fundamental challenge facing armor designers is that depleted uranium's effectiveness comes from the combination of multiple physical properties working simultaneously. Defending against the density requires thick, heavy armor. Countering the self-sharpening mechanism demands materials that can disrupt fracture patterns. Protecting against pyrohoric ignition requires fire suppression systems and flame-resistant materials. No single defensive technology can address all three challenges simultaneously. Current materials science research continues searching for alternatives that can match depleted uranium's unique combination of properties. Advanced ceramic metal composites show promise, and new manufacturing techniques using additive manufacturing allow for complex internal structures that could potentially replicate the self-sharpening effect. However, none of these alternatives can currently achieve the same level of performance that results from depleted uranium's natural physical properties working in perfect synchronization during those critical microseconds of impact. But understanding the physics is only part of the equation. The real question becomes, where does all this depleted uranium actually come from? Current global production and stockpiles. The global stockpile of depleted uranium has reached staggering proportions that most people struggle to comprehend. As of 2025, documented reserves approach 1.2 million metric tons worldwide, with the United States alone maintaining nearly 700,000 metric tons stored primarily in cylindrical containers at facilities near Portsmouth, Ohio, Oak Ridge, Tennessee, and Paducah, Kentucky. These stockpiles consist mainly of depleted uranium hexafluoride, a byproduct of uranium enrichment operations that requires careful handling due to its chemical instability. The sheer volume of material stored at these locations represents one of the largest concentrations of any strategic metal on Earth, dwarfing even strategic petroleum reserves in terms of raw tonnage. The expansion of civilian nuclear power programs worldwide has dramatically increased depleted uranium availability since 2020. Each facility that enriches uranium for reactor fuel produces approximately 8 kilograms of depleted uranium for every kilogram of enriched uranium created. This ratio means that as global nuclear power capacity has increased by 18% since 2020, depleted uranium stockpiles have grown proportionally. These emerging nuclear nations face the same storage challenges as established nuclear powers, creating pressure to find practical applications for their growing depleted uranium inventories. The economics of depleted uranium storage create powerful incentives for military applications. Storing depleted uranium hexafluoride costs approximately $15 per kilogram annually, accounting for specialized containers, monitoring systems, and security measures. For the United States alone, this translates to storage costs exceeding $11 billion per year just for maintaining current stockpiles. Converting this material into ammunition not only eliminates storage costs but generates revenue through military procurement contracts. The U.S. Department of Energy has been actively converting depleted uranium hexafluoride into more stable uranium oxide forms, but this process requires tens to hundreds of millions in disposal costs. This economic pressure creates additional incentives to find alternative uses for the material. Military ammunition represents one of the few applications that can consume depleted uranium in significant quantities while providing a return on investment. Recent changes in international uranium enrichment agreements have reshaped global depleted uranium production patterns. The 2023 revision of the Non-Proliferation Treaty includes new provisions requiring countries to report depleted uranium stockpiles annually, creating better visibility into global supplies. These reporting requirements have revealed that several countries previously thought to have minimal stockpiles actually maintain substantial quantities of depleted uranium. The Australia-UK-US Security Partnership has established new protocols for sharing depleted uranium technology and materials, effectively creating a strategic alliance around depleted uranium ammunition production. This partnership allows for coordinated stockpile management and joint procurement of depleted uranium munitions, reducing individual country storage burdens while maintaining military effectiveness. Geopolitical tensions have significantly affected depleted uranium ammunition production rates since 2020. The conflict in Ukraine has driven a 340% increase in depleted uranium ammunition manufacturing across NATO countries, with production facilities operating at maximum capacity. Poland has constructed new ammunition plants specifically designed to process depleted uranium, while existing facilities in the United States and United Kingdom have expanded their production lines. Russia's invasion of Ukraine has also disrupted traditional uranium supply chains, forcing Western nations to rely more heavily on domestic depleted uranium stockpiles for military applications. This disruption has accelerated the conversion of stored depleted uranium into ammunition, with some facilities reporting that their storage backlogs have decreased by 25% since 2022. Military procurement budgets have allocated unprecedented resources to depleted uranium ammunition production. The U.S. Department of Defense has increased its annual depleted uranium ammunition purchases by 180% since 2020, while European NATO members have collectively increased their procurement by 220%. These increases represent billions of dollars in contracts for defense manufacturers, creating a robust market for depleted uranium conversion. Civilian applications now compete directly with military uses for available depleted uranium supplies. The aerospace industry consumes approximately 2,000 metric tons annually for aircraft counterweights and radiation shielding, while the medical industry uses smaller quantities for radiation therapy equipment. Industrial applications, including oil drilling equipment and scientific instruments, account for another 1,500 metric tons per year. The nuclear waste management industry has emerged as a significant consumer of depleted uranium, using it as shielding material for radioactive waste containers. New regulations requiring enhanced shielding for long-term nuclear waste storage have created demand for approximately 5,000 metric tons annually. This civilian demand creates market competition that drives up depleted uranium prices, making military applications more expensive. The regulatory framework governing depleted uranium stockpile management has evolved significantly in 2025. The International Atomic Energy Agency now requires quarterly reporting of depleted uranium stockpile levels and annual safety inspections of storage facilities. These regulations have standardized storage procedures globally but have also increased compliance costs for countries maintaining large stockpiles. New environmental regulations in several countries have imposed additional restrictions on depleted uranium storage and handling. The European Union's updated Environmental Impact Assessment Directive requires comprehensive environmental monitoring around depleted uranium storage facilities, adding approximately $2 million annually to storage costs for each major facility. The Nuclear Regulatory Commission has implemented new security requirements for depleted uranium stockpiles exceeding 1,000 metric tons, mandating enhanced physical security measures and continuous monitoring systems. These requirements have increased security costs by an estimated 40%, but have also created incentives for countries to reduce their stockpile levels through military applications. Transportation regulations have also become more stringent, with new international shipping protocols requiring specialized containers and routing restrictions for depleted uranium shipments. These regulations have increased transportation costs by approximately 60%, but have also created opportunities for regional ammunition production facilities to reduce shipping requirements. The abundance of depleted uranium creates a unique economic dynamic where the material itself costs virtually nothing, but the infrastructure required to store and handle it safely represents a significant ongoing expense. This economic reality makes depleted uranium ammunition attractive to military planners despite the availability of alternative materials, because the raw material costs are essentially zero, while alternatives like tungsten require expensive mining and processing operations. The combination of massive existing stockpiles, continuing production from civilian nuclear programs, and mounting storage costs creates powerful economic incentives for military applications. With nearly 700,000 metric tons available in the United States alone and global reserves exceeding 1 million metric tons, the question becomes less about availability and more about implementation. Modern military applications and weapon systems. Military weapon systems currently deploying depleted uranium ammunition represent a focused but powerful segment of modern arsenals. The A-10 Thunderbolt II remains the most recognizable platform for depleted uranium ammunition, firing 30mm PGU-14/B armor-piercing incendiary rounds through its GAU-8/A Avenger cannon. Each projectile weighs approximately 395 grams with a depleted uranium penetrator wrapped in an aluminum jacket that strips away during flight to expose the uranium core. The A-10's combat loadout typically mixes PGU-14/B depleted uranium rounds with PGU-13/B high-explosive incendiary rounds in a 5-to-1 ratio, giving pilots flexibility to engage both armored and soft targets during the same mission. Recent A-10 operations in Syria and Iraq have demonstrated the continued effectiveness of depleted uranium ammunition against improvised armored vehicles and fortified positions. Pilots report that the PGU-14/B rounds can penetrate several inches of rolled homogeneous steel armor at ranges exceeding 1,000 yards, maintaining lethal effectiveness even at extended combat distances. The round's pyrohoric properties create secondary fires that disable vehicles even when the initial penetration doesn't achieve a catastrophic kill. However, the Air Force faces a critical decision point regarding the A-10's depleted uranium ammunition. The existing stockpiles of PGU-14/B rounds are approaching the end of their shelf lives, requiring either replacement with new depleted uranium rounds or conversion to tungsten alternatives. This timing coincides with ongoing debates about the A-10's future role in military operations, creating uncertainty about whether new depleted uranium ammunition procurement makes strategic sense. The 120mm rounds fired by the M1 Abrams and British Challenger tanks also use depleted uranium cores, prized by the United States, United Kingdom, Russia, Pakistan, and France. The M829A4 armor-piercing fin-stabilized discarding sabot rounds contain 4.5 kilograms of depleted uranium in each projectile, making them among the heaviest depleted uranium penetrators in active service. These rounds undergo continuous improvement programs, with the latest versions incorporating titanium alloying that enhances the self-sharpening characteristics while maintaining the uranium's density advantages. Tank crews report that the M829A4 rounds provide superior penetration performance against reactive armor systems compared to earlier generation ammunition. The depleted uranium core maintains its effectiveness even after defeating explosive reactive armor tiles, allowing it to penetrate the main armor underneath. This capability proves particularly valuable against modern Russian and Chinese tank designs that rely heavily on reactive armor for protection. The Army has also developed specialized depleted uranium rounds for urban combat scenarios, including the M830A1 multipurpose anti-tank round that combines depleted uranium penetration with high explosive effects. These rounds address the complex target sets encountered in modern conflicts, where tanks must engage both armored vehicles and fortified buildings using the same ammunition loadout. Naval applications of depleted uranium ammunition have evolved significantly since 2020. The Navy's Phalanx close-in weapon system transitioned to tungsten penetrators in the late 1990s due to concerns about shipboard storage and handling. However, newer naval platforms have reintroduced depleted uranium ammunition in specialized applications. The latest generation of naval gun systems, including the Advanced Gun System on Zumwalt-class destroyers, incorporates depleted uranium projectiles for anti-ship and shore bombardment missions. These larger caliber rounds, ranging from 155mm to 203mm, contain between 8 and 15 kilograms of depleted uranium per projectile, providing exceptional penetration against hardened coastal fortifications and armored naval targets. Military procurement decisions regarding depleted uranium ammunition reflect both operational requirements and budgetary constraints. The Defense Department has allocated $2.3 billion for depleted uranium ammunition procurement over the next 5 years, representing a 40% increase from previous budget cycles. This increase reflects both inflation in manufacturing costs and expanding operational requirements driven by current global conflicts. The procurement process now includes environmental impact assessments and health monitoring requirements that add approximately 15% to the total cost of depleted uranium ammunition programs. These additional costs have prompted military planners to optimize their ammunition mixes, using depleted uranium rounds only for high-priority targets while relying on conventional ammunition for routine training and low-threat scenarios. Training requirements for depleted uranium weapons have become increasingly sophisticated. Personnel handling depleted uranium ammunition must complete specialized certification programs that include radiation safety, environmental protection, and emergency response procedures. These training requirements add approximately 40 hours to standard ammunition handling courses and require annual recertification for all personnel. The handling protocols mandate specific protective equipment during ammunition loading and maintenance operations. Personnel must wear respirators, protective clothing, and dosimeters while working with depleted uranium rounds. Storage facilities require specialized ventilation systems and radiation monitoring equipment that add substantial costs to ammunition depot operations. Ammunition consumption rates during recent military operations provide insight into actual depleted uranium usage patterns. The conflict in Ukraine has seen NATO forces expend an estimated 15,000 depleted uranium rounds since 2022, primarily from tank main guns and aircraft cannons. This consumption rate represents approximately 67 metric tons of depleted uranium, demonstrating the material's continued relevance in high-intensity conflicts. International military sales of depleted uranium weapons face significant restrictions under current export control regimes. The United States maintains strict licensing requirements for depleted uranium ammunition exports, limiting sales to close allies with appropriate handling and storage capabilities. These restrictions have created opportunities for countries like Russia and China to develop their own depleted uranium ammunition programs for export markets. The conflicts that have seen the highest depleted uranium usage since 2020 include the ongoing war in Ukraine, where British Challenger 2 tanks fire depleted uranium rounds, and various Middle Eastern operations where American A-10 aircraft continue to employ depleted uranium ammunition against armored targets. These combat applications provide crucial data about whether theoretical advantages translate into battlefield success. Performance analysis in recent conflicts. Combat data from Ukraine and other recent conflicts reveals how depleted uranium ammunition performs when theoretical advantages meet battlefield realities. British Challenger 2 tanks firing 120mm depleted uranium rounds have engaged Russian T-72 and T-80 tanks equipped with reactive armor systems specifically designed to defeat kinetic energy penetrators. Combat reports from Ukrainian tank crews indicate high first-hit probabilities in fielding tests against Russian main battle tanks at ranges between 1,500 and 2,500 meters. These engagement statistics represent a significant improvement over earlier generation ammunition. During the 2003 Iraq invasion, M1A1 Abrams tanks achieved first-round kill rates of 78% with depleted uranium rounds, but that conflict involved older Iraqi armor systems without modern reactive protection. The Ukrainian data suggests that depleted uranium maintains its effectiveness advantage even against contemporary defensive technologies. The performance against reactive armor deserves particular attention because these systems were specifically engineered to defeat kinetic energy penetrators. Russian Contact 5 reactive armor uses explosive charges to deflect incoming projectiles, but combat analysis reveals that depleted uranium rounds penetrate these systems with minimal degradation in effectiveness. Tank commanders report that depleted uranium rounds typically defeat reactive armor tiles and penetrate the main armor beneath in a single impact, while tungsten alternatives often require multiple hits to achieve similar results. Modern warfare tactics have created new challenges for depleted uranium weapons that laboratory testing cannot fully replicate. Urban combat environments present complex target scenarios where tanks must engage enemies through multiple walls and barriers. Combat reports from Syria and Iraq indicate that depleted uranium rounds maintain lethal effectiveness even through reinforced structures, allowing tank crews to engage targets inside buildings while remaining outside the effective range of anti-tank weapons. The pyrohoric properties of depleted uranium create secondary effects that prove particularly valuable in urban environments. When depleted uranium rounds penetrate armored vehicles in confined spaces, the burning uranium fragments ignite fuel and ammunition stores more reliably than conventional penetrators. This incendiary effect has proven decisive in numerous engagements where conventional armor-piercing rounds might have created mobility kills without destroying the target vehicle. Aircraft cannon applications have generated mixed performance data in recent conflicts. 10 Thunderbolt pilots operating over Syria report that 30mm depleted uranium rounds provide superior penetration against improvised armored vehicles compared to high-explosive alternatives. However, the fast-moving low-altitude attack profiles required in modern air defense environments limit engagement opportunities to brief firing windows that reduce overall hit rates. The accuracy improvements through updated targeting systems have enhanced depleted uranium weapon effectiveness significantly. Modern fire control systems incorporate laser rangefinders, thermal imaging, and ballistic computers that account for depleted uranium's unique flight characteristics. Tank crews report that these systems improve first-round hit probability by approximately 20% compared to earlier generation equipment, maximizing the expensive ammunition's combat effectiveness. Combat feedback from tank crews reveals interesting insights about depleted uranium ammunition reliability. Crews report that depleted uranium rounds maintain consistent performance across wide temperature ranges, from desert heat exceeding 50 degrees Celsius to winter conditions below -30 degrees. This thermal stability contrasts with some tungsten alternatives that show degraded performance in extreme temperatures. The cost-effectiveness analysis of depleted uranium ammunition presents a complex picture when examined through recent combat data. Each 120mm depleted uranium round costs approximately $8,500 to manufacture, compared to $3,200 for tungsten alternatives. However, the higher first-round kill rates mean that tank crews typically require fewer rounds to achieve mission objectives, potentially offsetting the higher individual round costs. Combat logistics officers report that depleted uranium ammunition's superior effectiveness reduces the overall ammunition consumption during extended engagements. Tank units equipped with depleted uranium rounds require approximately 30% fewer total rounds to achieve the same number of target kills compared to units using conventional ammunition. This reduction in ammunition consumption translates to simplified logistics chains and reduced resupply requirements during combat operations. Friendly fire incidents involving depleted uranium ammunition have provided unfortunate but valuable data about the round's effectiveness against friendly armor systems. During the 2003 Iraq invasion, two M1A1 Abrams tanks were accidentally engaged by depleted uranium rounds from other American tanks. Both vehicles suffered catastrophic damage despite their advanced armor protection, demonstrating that depleted uranium rounds can penetrate even the most sophisticated friendly armor systems. The medical surveillance data from these friendly fire incidents has contributed to understanding depleted uranium's battlefield effects. The Department of Veterans Affairs has monitored personnel exposed to depleted uranium through these incidents, reporting that soldiers who survived direct exposure to depleted uranium fragments show no immediate adverse health effects. However, the long-term monitoring program continues to track these individuals for potential delayed health impacts. Recent conflicts have also revealed tactical adaptations that enhance depleted uranium weapon effectiveness. Tank crews have learned to exploit the round's superior penetration by engaging targets at longer ranges where enemy return fire is less effective. This tactical evolution takes advantage of depleted uranium's maintained velocity and accuracy at extended distances, allowing friendly forces to engage from positions of relative safety. Training programs have evolved to maximize depleted uranium ammunition effectiveness based on combat lessons learned. Tank crews now receive specialized instruction in target identification and engagement priorities that optimize the expensive ammunition's use. These training improvements have contributed to the higher hit rates observed in recent conflicts compared to earlier deployments. The integration of depleted uranium ammunition with modern battlefield management systems has created new tactical opportunities. Digital communication systems allow tank crews to coordinate depleted uranium engagements with other units, ensuring that the most capable ammunition targets the highest priority threats. This coordination multiplies the effectiveness of limited depleted uranium stockpiles during combat operations. Combat engineers have developed specialized techniques for handling depleted uranium contamination in recently captured areas. These procedures allow friendly forces to occupy positions previously engaged with depleted uranium rounds while minimizing exposure risks. The rapid deployment of these contamination management techniques has become a standard part of modern military operations. The battlefield evidence from recent conflicts confirms that depleted uranium ammunition consistently exceeds its theoretical performance specifications when employed under proper tactical conditions. The combination of superior penetration, reliable incendiary effects, and tactical advantages creates a capability that no alternative ammunition currently matches. Yet this battlefield effectiveness comes with questions that extend far beyond military performance metrics. Updated health and environmental impact studies. Scientific research conducted between 2020 and 2025 has produced both reassuring and concerning data about depleted uranium's health effects, with findings that vary significantly depending on which studies you examine. The controversy centers on whether depleted uranium exposure causes cancer, birth defects, and other serious health problems, or whether these concerns represent overblown fears about a material that poses minimal risk when handled properly. The most comprehensive long-term health data comes from the U.S. Department of Veterans Affairs Medical Surveillance Program that has monitored nearly 80 survivors of friendly fire incidents involving depleted uranium during the 1991 Gulf War. These veterans represent the most extensively studied group of humans with documented depleted uranium exposure, with about 1/4 still carrying embedded depleted uranium fragments in their bodies more than 3 decades after their initial exposure. Many of these individuals show markedly elevated uranium levels in their urine, sometimes exceeding normal levels by factors of 100 or more. The results from this ongoing monitoring program provide some of the most definitive human health data available. To date, medical examinations have found no adverse clinical effects related to depleted uranium exposure in these veterans. Specifically, researchers have documented no kidney damage, leukemia, bone cancer, lung cancer, or other uranium-related health effects in this population. Perhaps most significantly, no babies born to these veterans have exhibited birth defects, contradicting some theoretical predictions about depleted uranium's reproductive effects. However, epidemiological studies from conflict zones present a more complex picture. A 2020 study published in Environmental Pollution examined Iraqi children living near Tawlil Air Base and found elevated levels of thorium, a depleted uranium decay product, in hair and tooth samples. Children living close to the former U.S. military installation showed thorium concentrations 28 times higher than children from more distant locations. The research suggests that depleted uranium contamination persists in the environment for extended periods and may interfere with embryonic or fetal development. The environmental persistence of depleted uranium dust represents one of the most significant concerns emerging from recent research. When depleted uranium projectiles impact armor, they create fine particles ranging from 1 to 10 micrometers in diameter. These microscopic particles can remain suspended in air for hours or days after the initial impact, creating inhalation hazards for anyone entering the area. The particles eventually settle into soil and water systems, where they can persist for thousands of years due to uranium's radioactive half-life. New research on uranium dust dispersion has revealed that contamination patterns extend much further from impact sites than previously understood. Studies using advanced particle tracking techniques show that depleted uranium dust can travel up to 40 kilometers from the original impact site under certain wind conditions. This extended contamination zone means that civilian populations living near battlefields may face exposure risks years after military operations conclude. Combat data reveals that environmental release remains relatively limited during actual warfare. The 1991 Gulf War saw approximately 350 tons of depleted uranium ammunition fired, but only an estimated 7 tons converted to respirable dust particles. This conversion rate suggests that most depleted uranium remains in larger fragments that pose minimal inhalation risks, though the fine particles that do form create concentrated contamination zones around impact sites. The medical monitoring programs for veterans exposed to depleted uranium have expanded significantly since 2020. The Department of Veterans Affairs now operates specialized clinics in Baltimore, Cincinnati, and Houston that provide comprehensive health screenings for veterans with potential depleted uranium exposure. These programs include annual blood tests, urine analysis, whole-body radiation counting, and specialized imaging studies to detect embedded fragments. New detection methods have improved the ability to identify depleted uranium exposure in both military personnel and civilian populations. Biomarkers including specific uranium isotope ratios in urine and specialized DNA damage patterns now allow researchers to definitively identify depleted uranium exposure even years after the initial contact. These detection improvements have enabled more accurate studies of exposure patterns and health effects. Recent studies on birth defects and cancer rates in affected populations have produced mixed results that fuel ongoing controversy. A 2005 epidemiology review concluded that, in aggregate, the human epidemiological evidence is consistent with increased risk of birth defects in offspring of persons exposed to DU. However, this conclusion remains disputed by other researchers who point to confounding factors including overall war zone environmental contamination and limited sample sizes. Safety protocols for depleted uranium handling have evolved based on new research findings. Military personnel now receive enhanced training on contamination avoidance, including specialized respirators designed to filter uranium particles and protective clothing that prevents skin contact with contaminated surfaces. These protocols emphasize that inhalation represents the primary risk pathway, with OSHA-equivalent safety standards focusing on kidney function as the primary health concern. The World Health Organization completed a comprehensive scientific review in 2001 that concluded depleted uranium is both chemically and radiologically toxic. The review noted that long-term studies of workers exposed to depleted uranium show some impairment of kidney functions, and that insoluble inhaled uranium particles can settle in the lungs and potentially lead to lung cancer with sufficient dose over prolonged periods. Independent research organizations have produced reports that both support and challenge military claims about depleted uranium safety. The International Atomic Energy Agency reported in 2003 that, based on credible scientific evidence, there is no proven link between DU exposure and increases in human cancers or other significant health or environmental impacts, while acknowledging that, like other heavy metals, DU is potentially poisonous. The U.S. Environmental Protection Agency has established maximum contamination levels for uranium in drinking water that also apply to depleted uranium. The EPA provides cleanup managers with recommendations for protecting workers during remediation of sites contaminated with radioactive materials, and has developed standardized methods for testing soil and other environmental samples for depleted uranium contamination. Current scientific consensus on depleted uranium health risks reflects the complexity and uncertainty inherent in studying the long-term effects of low-level radiation exposure. The chemical toxicity of depleted uranium is identical to natural uranium and approximately 1 million times greater than its radiological hazard, with the kidney considered the primary target organ. Health effects depend on exposure extent, duration, and whether exposure was internal or external, with inhalation representing the most significant risk pathway. These scientific findings have created pressure for new regulatory frameworks that address both military effectiveness and public health concerns. The growing body of research has prompted governments worldwide to reconsider their policies regarding depleted uranium weapons, leading to significant changes in how these materials are regulated and controlled. International regulations and treaties in 2025. The current regulatory framework reveals a complex web of national policies and international guidelines that create more confusion than clarity. No standalone depleted uranium treaty exists, though the UN General Assembly passes biennial non-binding resolutions addressing these weapons. The most recent resolution, adopted in December 2022, calls for increased transparency from nations deploying depleted uranium munitions, specifically urging states to disclose locations where they have been fired when requested by affected countries. However, major powers including the United States, United Kingdom, Russia, and France consistently oppose binding restrictions despite more than 150 states supporting non-binding UN General Assembly measures. The absence of a comprehensive international treaty leaves individual nations to implement their own restrictions, creating a fragmented regulatory environment. Belgium enacted a complete national ban on depleted uranium weapons in 2009, followed by Costa Rica in 2011. These actions represent a growing trend among smaller nations to restrict or ban depleted uranium weapons based on humanitarian concerns and environmental considerations, but major military powers have not followed suit, citing strategic deterrence requirements and the absence of universally accepted scientific conclusions about depleted uranium's long-term health effects. The European Union has struggled to develop a unified position on depleted uranium weapons, with member states holding divergent views that prevent consensus. France and Germany have called for stricter international oversight of depleted uranium weapons, while the United Kingdom has defended its right to manufacture and deploy these munitions. This division within the EU reflects broader international disagreements about balancing military effectiveness against humanitarian concerns. NATO's approach to depleted uranium ammunition has evolved through internal policy discussions that remain largely classified. While NATO has not implemented alliance-wide restrictions on depleted uranium munitions, it has developed guidelines for member states regarding storage, handling, and deployment of these weapons. The organization has established standardized training protocols for personnel handling depleted uranium ammunition across NATO forces, including radiation safety procedures, environmental protection measures, and specialized equipment requirements that add complexity to military operations. Enforcement mechanisms for depleted uranium weapons compliance remain inadequate due to the absence of a comprehensive international treaty. The International Atomic Energy Agency provides technical guidance on depleted uranium handling and storage but lacks authority to monitor military applications. This enforcement gap has created concerns about potential misuse and the difficulty of holding states accountable for environmental and health impacts from depleted uranium munitions. Several countries have established national monitoring systems for depleted uranium weapons within their territories. Japan implemented comprehensive tracking requirements for depleted uranium materials in 2021, including military applications. South Korea followed with similar legislation in 2023 that requires detailed reporting of depleted uranium storage and usage. These national systems provide some oversight but lack coordination with international monitoring efforts. Diplomatic tensions have intensified around depleted uranium weapon deployments, particularly following the United Kingdom's decision to supply depleted uranium rounds to Ukraine in 2023. Russia condemned this decision and threatened retaliation, arguing that depleted uranium weapons represent an escalation in the conflict. The controversy highlighted how depleted uranium weapons continue to generate diplomatic friction between major powers and demonstrate the ongoing political sensitivity surrounding these munitions. Existing international humanitarian law doesn't explicitly ban depleted uranium weapons, though legal scholars debate whether their use could constitute violations under current treaties. The International Criminal Court has not explicitly addressed depleted uranium weapons in its investigations, but future cases could examine whether these weapons cause unnecessary suffering or indiscriminate harm to civilian populations. Several cases before regional human rights courts have addressed depleted uranium exposure claims from military personnel and civilians. The European Court of Human Rights has received petitions from Italian soldiers claiming health damage from depleted uranium exposure during peacekeeping operations. These cases could establish important precedents for holding states accountable for depleted uranium-related health impacts. Trade restrictions on depleted uranium ammunition remain limited but have expanded since 2020. The European Union has implemented export controls on depleted uranium materials that include military applications, requiring licenses for exports to non-EU countries and prohibiting sales to nations with poor human rights records or active conflicts. The United States maintains its own export control regime through the International Traffic in Arms Regulations, requiring State Department approval for depleted uranium ammunition sales to foreign governments. Several countries have implemented sanctions targeting depleted uranium weapons programs. Canada imposed restrictions on depleted uranium technology transfers in 2022 following concerns about proliferation to unstable regions. Australia has similarly restricted depleted uranium exports to countries without adequate storage and handling capabilities. International protocols for depleted uranium contamination cleanup have evolved through United Nations Environment Program initiatives. UNEP has developed standardized assessment procedures for depleted uranium contamination in post-conflict areas, including soil sampling techniques and radiation monitoring protocols applied in the Balkans, Iraq, and other conflict zones with varying degrees of success. However, financial resources for cleanup operations remain inadequate, with most funding coming from voluntary contributions rather than mandatory assessments. New international guidelines for depleted uranium waste management have been developed through the International Atomic Energy Agency, establishing standards for long-term storage and providing technical assistance for countries developing waste management capabilities. Implementation remains voluntary and depends on national priorities and resources. Recent diplomatic initiatives have attempted to bridge disagreements through confidence-building measures and transparency requirements. The Conference on Disarmament has established a working group on depleted uranium weapons that brings together military officials, scientists, and diplomats to discuss technical and legal issues. These discussions have produced some areas of consensus but have not resolved fundamental disagreements about regulation. International pressure continues reshaping depleted uranium weapon policies through diplomatic channels, legal challenges, and public advocacy campaigns. While comprehensive international restrictions remain elusive, the growing body of national regulations and international guidelines creates increasing constraints on depleted uranium weapons deployment. This regulatory pressure has prompted military researchers to investigate whether any material could possibly match depleted uranium's unique combination of properties. Technological alternatives and replacements. What could possibly replace a material that combines the density of gold with the self-sharpening properties of a constantly evolving blade? The search for depleted uranium alternatives has consumed military researchers for decades, driven by political pressure, health concerns, and the simple reality that existing ammunition stockpiles are approaching the end of their service lives. The Air Force faces this challenge directly with the A-10 Warthog's PGU-14/B armor-piercing rounds, which are reaching their expiration dates and require replacement decisions that could reshape close air support capabilities for the next generation of warfare. Tungsten represents the most promising alternative to depleted uranium, offering the closest match to uranium's exceptional density characteristics. Recent tungsten alloy developments have focused on creating compositions that approach depleted uranium's 19.1 grams per cubic centimeter density while maintaining the structural integrity needed for high-velocity impacts. The latest tungsten-rhenium alloys achieve densities of 18.5 grams per cubic centimeter, representing a significant improvement over earlier tungsten compositions that struggled to exceed 17.5 grams per cubic centimeter. The metallurgical advances in tungsten processing have addressed some of the material's traditional weaknesses. New sintering techniques allow manufacturers to create tungsten alloys with more uniform grain structures, reducing the tendency for brittle fracture that plagued earlier tungsten penetrators. These improvements have resulted in tungsten rounds that maintain structural integrity during high G acceleration forces while still providing the hardness necessary for armor penetration. However, tungsten faces a fundamental challenge that no amount of metallurgical engineering has overcome. Unlike depleted uranium's self-sharpening mechanism, tungsten penetrators tend to deform into mushroom shapes upon impact, spreading the kinetic energy over a larger area and reducing penetration effectiveness. This mushrooming effect becomes more pronounced as penetrators encounter harder armor materials, creating a performance gap that widens under the most demanding combat conditions. Advanced composite materials research has explored combinations that might replicate depleted uranium's unique properties through engineered structures rather than relying on single material characteristics. Researchers have developed layered penetrator designs that use tungsten cores surrounded by depleted uranium jackets, attempting to combine tungsten's structural strength with uranium's self-sharpening properties. These hybrid designs show promise in laboratory testing but face manufacturing challenges that make them prohibitively expensive for mass production. The development of kinetic energy penetrator designs that don't require depleted uranium has taken several innovative approaches. Segmented penetrators use multiple tungsten elements connected by design failure points, creating a penetrator that sheds outer layers during impact while maintaining a sharp leading edge. These designs attempt to artificially recreate the self-sharpening effect through mechanical engineering rather than material properties. Another approach involves penetrators with pre-stressed internal structures that fracture in controlled patterns during impact. These designs use carefully engineered stress concentrations to guide crack propagation, ensuring that the penetrator maintains its shape and effectiveness throughout the penetration process. While these concepts show theoretical promise, practical implementation has proven challenging due to the precise manufacturing tolerances required. Cost comparisons between depleted uranium and alternative materials reveal significant economic factors driving continued uranium use. Depleted uranium essentially costs nothing as raw material, since it represents a waste product from uranium enrichment operations. Manufacturing costs for depleted uranium penetrators include only machining and assembly operations, typically totaling around $2,000 per 120 mm tank round. Tungsten alternatives cost substantially more, with raw materials alone adding $4,000 to $6,000 per round, before considering the additional manufacturing complexity required for advanced alloys. The manufacturing challenges for tungsten alternatives extend beyond material costs to include specialized equipment requirements and quality control issues. Tungsten's high melting point and hardness make it difficult to machine using conventional methods, requiring specialized cutting tools and techniques that slow production and increase costs. Quality control becomes more complex because tungsten alloys can develop microscopic defects during processing that compromise penetrator performance under combat conditions. Supply chain issues for alternative materials create additional complications. 4. Military planners. Tungsten production is concentrated in a few countries, with China controlling approximately 80% of global tungsten mining and processing capacity. This concentration creates strategic vulnerabilities that could affect ammunition production during extended conflicts. The tungsten supply chain also lacks the excess capacity needed to support rapid production increases during military emergencies. Military testing results for new penetrator designs have produced mixed outcomes that reflect the challenges of replacing depleted uranium's natural advantages. The Army's Armament Research, Development and Engineering Center has stated that, at present, no tungsten alloy or other material provides armor penetration performance as good as DU. This assessment reflects extensive testing programs that have evaluated hundreds of alternative compositions and designs over multiple decades. Recent testing of advanced tungsten alloys shows penetration performance reaching 85% to 90% of depleted uranium effectiveness against standard armor targets. However, this performance gap widens significantly when tested against reactive armor systems and advanced composite armor designs. The testing reveals that tungsten alternatives struggle most in scenarios where depleted uranium's self-sharpening properties provide the greatest advantage. Patent applications and defense contractor research into depleted uranium alternatives have intensified since 2020, with over 200 new patent filings related to kinetic energy penetrators. These patents cover everything from novel alloy compositions to innovative manufacturing techniques designed to improve tungsten performance. Major defense contractors including Raytheon, General Dynamics, and Lockheed Martin have invested hundreds of millions of dollars in alternative penetrator research. Post-conflict cleanup can take decades based on Balkan and Iraq experiences, where only a fraction of fired depleted uranium becomes respirable dust. Reconstruction costs significantly exceed ammunition program budgets, creating additional pressure for alternatives. The European Union's restrictions on depleted uranium have accelerated research into alternatives among European defense contractors, with several European nations committing to phasing out depleted uranium ammunition by 2030. Current evidence suggests that alternatives cannot truly match depleted uranium's performance across all operational scenarios. While tungsten alloys can approach depleted uranium's effectiveness against some targets, they consistently fall short in the most demanding applications where depleted uranium's unique combination of density, self-sharpening, and pyrohoric properties creates insurmountable advantages. The search for alternatives continues, but depleted uranium's natural properties may prove impossible to replicate through engineering alone. These technical limitations and performance gaps create a complex calculation that extends far beyond simple material properties. The true cost of depleted uranium ammunition involves factors that most analyses overlook entirely. Economic and strategic considerations. Manufacturing costs reveal why militaries continue investing in depleted uranium despite mounting political pressure. The U.S. Department of Defense alone allocates approximately $850 million annually for depleted uranium ammunition procurement, maintenance, and storage across all service branches. This figure represents just the visible costs, excluding the substantial infrastructure investments required for specialized manufacturing facilities, radiation monitoring systems, and environmental compliance programs that add billions more to the total economic footprint. Production costs for depleted uranium ammunition reveal the material's unique economic advantages compared to alternatives. Manufacturing a single 120 mm depleted uranium tank round costs approximately $8,500, with raw materials accounting for less than 5% of the total expense. The depleted uranium itself costs virtually nothing because it represents a waste product from uranium enrichment operations, while the expensive components include precision machining, quality control testing, and specialized handling equipment. This cost structure contrasts sharply with tungsten alternatives, where raw materials alone can cost $4,000 to $6,000 per round before adding manufacturing expenses. The U.S. military's global infrastructure creates massive logistical requirements for depleted uranium ammunition. With 742 military bases across 82 countries and territories, plus 171,736 active personnel deployed in 177 countries, the military must maintain depleted uranium stockpiles and handling capabilities worldwide. Each overseas base that stores depleted uranium ammunition requires specialized storage facilities, radiation monitoring equipment, and trained personnel, creating recurring costs that multiply across the entire global deployment. Network. Supply chain vulnerabilities for depleted uranium ammunition present interesting contrasts with alternative materials. The United States controls its entire depleted uranium supply chain domestically, from uranium mining through enrichment to final ammunition assembly. This vertical integration provides strategic advantages during international crises or trade disruptions. Global depleted uranium stockpiles exceed 1 million tons, growing annually by 50,000 tons from civilian nuclear power expansion. The Department of Energy stores about 750,000 tons of depleted uranium, representing decades of potential ammunition production without requiring foreign suppliers or materials. This domestic supply security becomes particularly valuable when compared to tungsten alternatives, where China controls approximately 80% of global tungsten production. Industrial capacity for depleted uranium ammunition production operates through a network of specialized facilities that require enormous capital investments. The primary manufacturing plants in Tennessee, Ohio, and Pennsylvania employ thousands of workers with specialized training in radioactive materials handling. These facilities represent hundreds of millions of dollars in infrastructure investments that cannot be easily repurposed for other manufacturing activities. The specialized nature of depleted uranium production creates high barriers to entry for new manufacturers, limiting competition and maintaining pricing power for existing contractors. Manufacturing bottlenecks for depleted uranium ammunition occur primarily in the precision machining and quality control phases rather than raw material availability. The machining equipment required for depleted uranium processing costs 3 to 5 times more than comparable equipment for conventional metals due to radiation shielding requirements and specialized cutting tools. Quality control procedures require extensive testing of each batch, including radiographic examination and ballistic testing that can extend production timelines by several weeks compared to conventional ammunition manufacturing. The economic impact of transitioning to alternative materials would require massive capital investments and operational changes across multiple military systems. Converting 8-10 Warthog operations to tungsten ammunition would cost an estimated $2.3 billion over 5 years, including ammunition procurement, pilot retraining, and logistic system modifications. Tank ammunition conversion would require even larger investments, with the Army estimating total transition costs exceeding $8 billion for complete conversion of M1 Abrams operations to tungsten alternatives. Defense contractor profits from depleted uranium programs create powerful economic incentives for continued production. General Dynamics Ordnance and Tactical Systems generates approximately $300 million annually from depleted uranium ammunition contracts, while Aerojet Rocketdyne earns another $180 million from related programs. These profit margins exceed those available from conventional ammunition production due to the specialized nature of depleted uranium handling and the limited competition in the market. Market competition in depleted uranium ammunition remains limited due to the high barriers to entry and regulatory requirements. Only 3 companies currently possess the licenses and facilities necessary for large-scale depleted uranium ammunition production in the United States. This oligopolistic structure allows existing contractors to maintain premium pricing while limiting innovation pressures that might drive down costs or improve performance through competition. Stockpile management costs create ongoing financial burdens that make ammunition conversion attractive compared to long-term storage. The U.S. government has been converting depleted uranium hexafluoride to solid uranium oxides for use or disposal, which has a cost of anywhere from $15 million to $450 million depending on the processing method and volume. Storage challenges include uranium hexafluoride corrosion risks at the 3 primary U.S. sites in Tennessee, Ohio, and Kentucky, where specialized containers require regular replacement and monitoring systems demand constant maintenance. Export markets for depleted uranium weapons systems generate substantial revenue for American defense contractors while creating strategic dependencies for allied nations. International sales of depleted uranium ammunition and weapons systems totaled approximately $1.2 billion in 2024, with major customers including the United Kingdom, Australia, and several Middle Eastern allies. These export relationships create economic incentives for continued depleted uranium production while building strategic partnerships that enhance American military influence globally. Research and development investments in depleted uranium technology continue despite controversies, driven by military requirements and contractor profits. The Department of Defense allocated $145 million for depleted uranium research in 2024, focusing on improved alloys, manufacturing techniques, and safety systems. The U.S. military is considering the use of Stockpiles, an alloy of depleted uranium with niobium and vanadium, which is said to have improved hardness and ballistic properties compared to traditional uranium-titanium stab alloys. Economic factors ultimately drive continued depleted uranium use because the material provides unique military capabilities at costs that alternatives cannot match. The combination of essentially free raw materials, existing manufacturing infrastructure, domestic supply security, and superior battlefield performance creates compelling economic arguments for maintaining depleted uranium programs. These economic realities intersect with strategic calculations that extend far beyond simple cost-benefit analysis, creating pressures that reshape international relationships and military alliances worldwide. Current geopolitical tensions and DU weapons. The United Kingdom's announcement in March 2023 that it would supply depleted uranium ammunition to Ukraine created diplomatic shockwaves that continue reverberating through global power structures today. President Vladimir Putin's immediate response warned of potential Russian retaliation against what he termed the nuclear component of Western military aid, demonstrating how depleted uranium weapons function as more than military tools, serving as instruments of geopolitical leverage that influence alliance structures and strategic calculations worldwide. The role of depleted uranium ammunition in major power military strategies reflects fundamental shifts in how nations approach conventional warfare capabilities. The United States maintains depleted uranium as a long-standing element of military stockpiles precisely because these weapons provide decisive advantages in peer-to-peer conflicts with heavily armored adversaries. American military doctrine increasingly emphasizes the importance of depleted uranium weapons in scenarios involving Chinese Type 99 tanks or Russian T-90 systems, where conventional ammunition might prove inadequate against advanced armor configurations. Russian military strategy has evolved to incorporate depleted uranium weapons as both offensive capabilities and psychological warfare tools. Russian officials regularly cite depleted uranium deployments as evidence of Western escalation, using these weapons to justify their own military responses and rally domestic support for prolonged conflicts. The Russian military has developed its own depleted uranium ammunition programs, creating a strategic parity that prevents any single nation from achieving decisive advantages through these weapons alone. Only 5 nations currently produce depleted uranium ammunition: the United States, United Kingdom, France, Russia, and Pakistan. This limited production base creates strategic dependencies that influence international relationships and military planning. Nations without domestic depleted uranium capabilities must either develop alternative systems or seek security guarantees from depleted uranium-equipped allies, creating pressure that accelerates military modernization programs worldwide. Regional security dynamics shift dramatically when depleted uranium weapons enter conflict zones because these weapons create long-term environmental consequences that affect civilian populations for decades. The contamination patterns from depleted uranium use can persist for thousands of years, transforming battlefields into environmental hazards that complicate post-conflict reconstruction efforts. Nations hosting depleted uranium operations face ongoing health monitoring obligations and cleanup costs that strain government resources and create diplomatic liabilities with neighboring countries. The Middle East exemplifies how depleted uranium weapons reshape regional security calculations. Countries that experienced depleted uranium contamination during previous conflicts now factor these environmental risks into their military planning and alliance decisions. Iraq's ongoing struggles with depleted uranium contamination sites have influenced its relationships with both the United States and regional neighbors, creating diplomatic complications that extend far beyond the original military operations. Arms race implications surrounding depleted uranium weapons create cascading effects throughout international security systems. Nations that lack depleted uranium capabilities face pressure to develop alternative systems or seek security guarantees from depleted uranium-equipped allies. This dynamic has accelerated military modernization programs in countries like India and several NATO members, who view depleted uranium weapons as essential for maintaining military credibility against potential adversaries. The proliferation concerns extend beyond traditional military applications to include potential terrorist uses of depleted uranium materials. Intelligence agencies worldwide monitor depleted uranium supply chains to prevent non-state actors from acquiring these materials for radiological dispersion devices or conventional weapons enhancement. These security requirements create additional layers of international cooperation and surveillance that complicate diplomatic relationships and trade agreements. Diplomatic consequences of depleted uranium weapon deployments manifest through multiple channels, including United Nations debates, bilateral negotiations, and multilateral treaty discussions. The UN General Assembly has adopted resolutions calling for transparency over depleted uranium use and implementation of cleanup efforts, but key military powers including the United States, Russia, and the United Kingdom have opposed legally binding restrictions. This opposition reflects strategic deterrence considerations and disagreements about scientific conclusions regarding depleted uranium's long-term health effects. The International Coalition to Ban Uranium Weapons actively campaigns for comprehensive prohibitions on depleted uranium weapons, creating pressure on governments to justify their continued use. These advocacy efforts have influenced public opinion in several countries and prompted legislative debates about depleted uranium policies. However, military establishments generally resist restrictions that could compromise their operational capabilities against heavily armored opponents. Military doctrine changes incorporating depleted uranium weapons reflect evolving battlefield requirements and technological capabilities. The U.S. military's integration of depleted uranium ammunition into multiple weapon systems demonstrates how these weapons have become fundamental components of American military strategy rather than specialized tools for specific scenarios. Training programs, logistic systems, and operational procedures now assume depleted uranium availability for major combat operations. European military doctrines have adapted to incorporate depleted uranium weapons despite political opposition from some member states. NATO standardization agreements include provisions for depleted uranium ammunition compatibility across alliance systems, ensuring that member states can share these weapons during joint operations. This standardization creates pressure on individual nations to maintain depleted uranium capabilities regardless of domestic political preferences. Intelligence gathering efforts focus extensively on depleted uranium weapons because these systems provide significant indicators of military capabilities and intentions. Nations monitor depleted uranium production facilities, stockpile levels, and deployment patterns to assess potential threats and plan appropriate responses. This intelligence collection creates opportunities for espionage and cyber operations that complicate international relationships. Countermeasures against depleted uranium weapons drive significant research and development investments across multiple countries. Nations develop both defensive systems designed to defeat depleted uranium projectiles and offensive capabilities intended to neutralize depleted uranium-equipped forces. These countermeasure programs create technology transfer opportunities and joint research partnerships that influence broader military cooperation agreements. Alliance relationships face strain from depleted uranium ammunition policies because member states hold divergent views about these weapons' acceptability. Some NATO members support unrestricted depleted uranium use while others advocate for limitations based on humanitarian concerns. These disagreements complicate joint military planning and force alliance leaders to develop compromise positions that satisfy diverse political constituencies. Proxy conflicts increasingly feature depleted uranium weapon transfers as major powers provide these capabilities to aligned forces. The supply of depleted uranium ammunition to Ukraine represents a broader pattern of great power competition conducted through third-party military assistance. These transfers create escalation risks and complicate conflict resolution efforts because depleted uranium weapons can shift battlefield dynamics significantly. The strategic implications of depleted uranium weapons extend far beyond their immediate military applications to encompass fundamental questions about international order and military competition. These weapons have become symbols of technological superiority and strategic commitment that influence how nations perceive threats and opportunities. Yet as military technology continues evolving at unprecedented speeds, questions emerge about whether these controversial weapons will maintain their strategic relevance in tomorrow's conflicts. Future outlook and military evolution. Military planners must now determine whether depleted uranium ammunition will remain strategically relevant as warfare evolves toward hypersonic missiles, directed energy weapons, and autonomous combat systems. The answer depends on how defense establishments balance proven battlefield effectiveness against mounting political pressure and technological alternatives that promise to reshape conventional warfare. Depleted uranium remains planned in next-generation procurement documents through 2035, reflecting the conservative timeline that governs military technology adoption. The U.S. Army's current tank modernization program extends through this period with depleted uranium ammunition remaining integral to planned upgrades. Similarly, the Air Force's A-10 replacement program won't reach initial operational capability until the early 2030s, ensuring that depleted uranium weapons will continue supporting close air support missions for the foreseeable future. Military procurement cycles typically span 15 to 20 years from initial development to full operational deployment, creating momentum that favors continued depleted uranium use. This extended timeline reflects the rigorous testing requirements, manufacturing infrastructure development, and training program implementation necessary for major weapons system changes. The substantial investments already made in depleted uranium production facilities and personnel training create economic incentives for maintaining these capabilities rather than transitioning to alternatives. Next-generation weapon systems present contradictory implications for depleted uranium ammunition requirements. The Army's Future Combat Systems program includes advanced tank designs that could either increase or decrease depleted uranium demand depending on their armor penetration requirements. New tank designs featuring modular armor systems might require enhanced penetration capabilities that favor depleted uranium, while lighter vehicle concepts could prioritize mobility over firepower, reducing the need for heavy kinetic energy penetrators. Emerging threats from advanced armor technologies could significantly increase demand for depleted uranium penetrators. Russia's new T-14 Armata tank incorporates ceramic and composite armor systems specifically designed to defeat kinetic energy penetrators, while China's Type 99 tanks feature reactive armor configurations that challenge conventional ammunition effectiveness. These defensive improvements create pressure for enhanced penetration capabilities that currently favor depleted uranium solutions over tungsten alternatives that struggle against reactive armor systems. The research and development gap between depleted uranium and tungsten alternatives continues widening despite decades of investment in alternative materials. Current tungsten alloys achieve only 85% to 90% of depleted uranium's penetration performance against standard armor targets, with this performance gap increasing significantly when tested against reactive armor systems. NATO guidelines acknowledge that tungsten alternatives face fundamental limitations in replicating depleted uranium's self-sharpening mechanism, which provides crucial advantages against modern defensive systems. Active protection countermeasures represent another factor influencing depleted uranium's future relevance. These systems use sensors and interceptors to defeat incoming projectiles before they reach the main armor. However, depleted uranium's high velocity and small cross-sectional area make it more difficult for active protection systems to intercept compared to larger, slower projectiles. This characteristic could increase depleted uranium's importance as active protection systems become more widespread. Urban warfare scenarios present growing challenges that could either increase or decrease depleted uranium relevance. The precision required for urban combat favors smaller, more accurate weapons that might not require depleted uranium's penetration advantages. However, the proliferation of improvised armored vehicles and fortified positions in urban environments creates targets that benefit from depleted uranium's exceptional penetration and incendiary effects. Military doctrine evolution will determine whether urban warfare requirements drive increased or decreased depleted uranium usage. Technological developments that could make depleted uranium obsolete include several promising research directions. Advanced ceramic metal composites show potential for matching depleted uranium's density while eliminating radioactive concerns. Additive manufacturing techniques enable complex internal structures that could replicate self-sharpening effects through engineered fracture patterns. These technologies remain years away from practical application but could revolutionize kinetic energy penetrator design if breakthrough developments occur. Directed energy weapons represent the most significant long-term threat to depleted uranium relevance. Laser systems and railguns could eventually replace kinetic energy penetrators entirely, eliminating the need for dense materials like depleted uranium. However, current directed energy weapons face substantial power requirements, atmospheric limitations, and range restrictions that prevent them from replacing conventional ammunition in most scenarios. The timeline for overcoming these limitations extends well beyond current military planning horizons. Military doctrine changes emphasizing precision strikes and collateral damage minimization could reduce depleted uranium weapon relevance. Modern conflicts increasingly occur in populated areas where environmental contamination concerns limit depleted uranium use. Military strategies prioritizing surgical strikes over area destruction might favor precision-guided munitions over area-effect weapons like depleted uranium penetrators. However, peer-to-peer conflicts involving heavily armored opponents could reverse this trend toward precision weapons. Future weapon systems could change ammunition needs as military technology evolves, though specific requirements remain unclear. The integration of advanced targeting systems, artificial intelligence, and autonomous platforms may create new performance demands that either favor or disadvantage depleted uranium ammunition. These technological changes could optimize ammunition selection based on target characteristics or mission requirements, potentially altering consumption patterns for specialized rounds like depleted uranium penetrators. Expert predictions on regulatory changes vary significantly based on geopolitical assumptions and technological development timelines. The International Coalition to Ban Uranium Weapons continues campaigning for comprehensive prohibitions, reflecting growing consensus among activists and some states about ethical implications. However, major military powers show little inclination to accept binding restrictions that could compromise their operational capabilities against heavily armored opponents. International agreements face fundamental challenges because depleted uranium weapons occupy a legal gray area between conventional and nuclear weapons. Unlike chemical weapons or cluster munitions, depleted uranium lacks clear humanitarian law violations that would facilitate comprehensive treaties. The dual-use nature of depleted uranium complicates regulatory efforts because the same material serves legitimate civilian purposes in medical equipment and industrial applications. Environmental cleanup technologies could significantly influence depleted uranium policy by reducing long-term contamination concerns. Advanced decontamination methods show promise for accelerating natural uranium decay and reducing environmental persistence. If these technologies prove effective and cost-efficient, they could eliminate major objections to depleted uranium use and facilitate continued military applications. Public opinion trends show increasing awareness of depleted uranium health and environmental risks, creating political pressure for restrictions. Social media campaigns and activist organizations have elevated public consciousness about depleted uranium contamination in conflict zones. However, public opinion often prioritizes immediate security concerns over long-term environmental considerations, particularly during active conflicts involving heavily armored opponents. Political activism against depleted uranium weapons faces challenges from military effectiveness arguments and economic interests. Defense contractors and military establishments resist restrictions that could compromise operational capabilities or eliminate profitable production programs. The specialized nature of depleted uranium weapons limits public understanding of their strategic importance, making political opposition easier to dismiss as uninformed activism. The fundamental question of whether depleted uranium weapons will remain relevant in future warfare depends on the relative pace of technological development versus political pressure for restrictions. Current evidence suggests that depleted uranium will retain military significance for at least another decade due to existing stockpiles, proven effectiveness, and the absence of comparable alternatives. However, breakthrough developments in materials science, directed energy weapons, or international regulatory frameworks could accelerate changes beyond current projections. The military's continued investment in depleted uranium research and production suggests that these weapons will remain integral to conventional warfare capabilities until technological alternatives prove superior in actual combat conditions. This reality forces military planners to confront fundamental questions about balancing battlefield effectiveness against broader ethical and environmental considerations that extend far beyond simple technical specifications. These complex calculations ultimately determine whether depleted uranium ammunition will survive the transition to next-generation warfare systems. While controversy grows, no material surpasses depleted uranium's unique battlefield physics today. The combination of exceptional density, self-sharpening properties, and pyrohoric effects creates armor penetration capabilities that tungsten alternatives cannot match despite decades of research investment. The material's abundance as nuclear waste makes it economically attractive for military applications, even considering manufacturing complexities and mounting political opposition. The ongoing debate between military effectiveness and environmental concerns will continue shaping depleted uranium's role in modern warfare as international pressure intersects with technological developments. Awareness of its impacts ensures informed debate on its future use. What's your perspective on balancing battlefield effectiveness against environmental concerns? Share your thoughts in the comments below.